Hello guys, I am Sumit Kumar Das and welcome back to SK Neuron. You are watching the next episode in our LangChain course playlist. Today we'll be deep diving into one of the most crucial concepts in generative AI, that is embeddings. We'll start with the absolute basics, what embeddings are, what vectors means, and why they matter. Then I will show you how to work with embeddings in LangChain, including some of the powerful methods like caching techniques that will save your time and money in real-time applications. And of course, everything will be demonstrated with live code so that you can see exactly how it all works. So let's jump in.
Alright, let's start with the fundamentals. What is an embedding? Embedding is a way of representing text in a form of numbers. Specifically for text embedding, because there are different types of embedding. There are something called as character embedding, where I will represent each character of a sentence or paragraph into one numbers. While there is called as word embedding, where I will convert each word into certain numbers. And then finally there is text embedding. Here I will convert the whole paragraph or the whole set of text or a set of sentences or a set of words into certain numbers. For example, let's take an example. Machine learning is fascinating. Okay? So first, in character embedding, I will represent each character as one number. So in this word machine, I will represent one M as one number, A as one number, C as one number. Similarly, I will represent each character as one number. But when it comes to word embedding, I will represent this complete one as one number. Let me represent as N1 as that particular number. I will represent a learning as one number. I will represent is as one number and fascinating as one number. But when it comes to text embedding, I will represent the whole paragraph or the whole set of text available into a set of numbers that is called as vectors. Vectors will be like a set of numbers. For example, zero point 0.4, zero point 0.5, minus zero point 0.6, zero point 0.7. Now you might be wondering, why a list of numbers? Why not just a single number? That's where somewhere, and that's why we just have one more concept called as embedding size, or sometimes also called as dimension, right? Or dimensionality of the model. Why we are not representing with only single number? Because a single number can only capture one dimension of meaning. For example, you have a word, let me say you have a word dog. Dog can be related with an animal. Dog can be related with a pet. Dog can be related with who barks. Dog can be related with who has four legs. One simple word dog, it has how many dimensions? How many meanings it can, or how many related words it can have? So to capture all the different aspects, we are assigning multiple numbers here. So here I have assigned four numbers, means we are representing these sets of text in four dimensions, where it will try to capture different aspect of the meaning. So what's the general size, or what is the general embedding model dimension will be? Sometimes it can start with numbers like 384 for small models or 768. These are for smaller and faster model. While you goes to bigger model, for example, let me take OpenAI's ADA 002, right? There you will have something like 1536 dimension. Or let me take example of Gemini model, right? Gemini embedding model. There you will have 3072 dimensions. See, one set of text is representing in 3072 dimension with 3072 aspects, because text itself is very complex. There is grammar, there is so much of thing to understand one text, right? With you just change some letters, you just change some words, it will give you some different sets of meaning. Now let me embed these three sentences. I love dogs. Next, let me keep one more sentence. Dogs are amazing pets. And third one is Python is a programming language. So here I have three sentences, right? The first two sentence, let me say as E1 and E2, right? These two will have similar to each other because they are giving almost same meaning or they are closer to each other. While the first sentence and the third sentence, right? They are different to each other. So this is what called as vector space. What is vector space? Where a space where different vectors which represent same sets of meaning will cluster together, while vectors having different sets of meaning will be spread apart. Okay, so e1 and e3, e1 and e3 will be at different sets of point, while e1 and e2 will be close to each other. Then how do we know that? I know as a human that e1 and e2 are same. I know as a human that e1 and e3 are different. But how a machine will know? How computer will understand that e1 and e2 are same? So for that, we have to do some or calculate some similarity score between e1, e2 and e3. And similarity score has to be same or uh, similarity score has to be high between e1 and e2, and it has to be low between e1 and e3. So what are the different methods to calculate the similarity between them? So to calculate similarity score, first is equidistant distance. What is equidistant distance? It is a straight line distance between two points. For example, you have a point having x1 and x2, and you have another point having x3 and x4. So what is the distance between them? So this distance will be x3 minus x1 square plus x4 minus x2 square root, right? So this is equidistant distance. Then, so this is one way. So less the distance, they are more similar, right? If two vectors or two sets of this is one set, you can consider this as one vector, this is as another vector, right? Let this is vector 1, this is vector 2. So less the distance will be, more the similar they will be, right? So here, for vectors to be become more similar, the distance has to be less between them, right? Then only they can be close, right? In vector space, for similar embedding, for similar vectors they should place together, right? They should place together. That's why distance should be less. Then next is dot product. So if you have two vectors, vector v1 and vector v2, so how you will calculate the dot product? So dot product means how much one vector project into another vector. So here you have to text two equal length vector and it will return a single scale value, or this is sometimes also called as inner product. Let's see here, v1 has x1 and x2 points while v2 has x3 and x4. So for that, dot product will be summation of multiplication of v1 v2, right? That will be x1 x3 plus x2 x4. So here you are trying to measure how one vector is project onto another, right? So here, more higher the value, more the vector will be similar to each other, because here we are calculating by multiplying the corresponding elements of each vector. So here first vector have two dimensions, second vector also have two dimensions, so I am multiplying. So here always it has to be of the same, both vector has to be of same dimension, then only you can measure this for everything, for equidistant, for dot product. Then we will go to our third one. So then there is another one that is called as cosine similarity, and this is mostly used in every industry nowadays. The cosine similarity, it measures the angle between two vectors. Okay, so if we have b1 and b2, it will be b1 dot b2 divided by mod of b1 divided by mod, that is magnitude of them, magnitude of vector 1 and magnitude of vector 2. And here suppose b1 is equal to square root of x1 square plus x2 square, and v2 will be square root of x3 square plus x4 square. And why this is more useful? Because it is taking both magnitude as well as direction between them, right? In dot product we are only taking the direction between them. In equivalent distance we are only taking the magnitude between them. But cosine similarity considers both magnitude and direction of the each vector. That's why this is more useful, and it can gives more meaningful representation than single dot product, or single only using dot product, or only using equivalent distance. So here again, more the value will be, higher the value, more they are similar to each other.
Alright, let's see this in action. I am going to show you exactly how embeddings transform text into vectors and how we use those vectors. But before that, I have already completed the LangChain setup with Gemini model in my notebook. But if you're not sure how to get started, check out the videos I have attached here, where I will walk you through entire LangChain setup using Python and demonstrated how to interact with different types of model in detail. First, let me import what we need. So first, I will import all the Gemini embedding model, that is Gemini embedding 001. Now, watch this. I am going to embed some text. If you see here, the dimension of this vector is 3072. It means my sentence become a vector with 3072 dimension. And each of these number represent some aspect of the meaning of this sentence. And let me print just first five. This just show how a vector looks like. So similarly, I will have more 3067 numbers or 67 dimension. And it is with respect to Gemini model. If you go to other model, be it OpenAI, Core, or Cloud embedding model, they will have different embedding size. Now, here is what is interesting. Let me embed three different sentences. Okay, but the first two sentences are about AIML and the third is about food. Let's see if the embeddings are captured properly or not. Okay, now I've run it. Let me see how many vectors are there. Three vectors. Three vectors for three pieces of text. First text, second text, and third text. And what are the size of each vector? It will be 3072. Okay. If you print all the three vector size, it will be same because all are coming from the Gemini embedding model. Now, to compare these vectors, we have to use similarity matrices. So let me show you how we can compare these vectors. So there are three similarity matrices: dot product, equivalent distance, and cosine similarity. Dot products measure the projection between the vectors. How one vector is projected with the other one. So higher the value, more similar they are. Using numpy dot. And second is equivalent distance that measures the straight line distance between both. And using, so that's why we are using normalization here. As they're measuring the distance, so the lesser the distance, they're more close to each other and more similar. But the cosine similarity that measures the angle between two vectors, it contains both magnitude and directions. So that's why it has it all both contains normalization as well as direction, that is dot product. And here, higher the value, more similar, because when as it is measures the angle between vector and it is measuring the cosine angle. So if the angle between them is less, it means they are more close to each other. So cos 0 is equal to 1. And when they are more far from each other, that is cos 90. When they are 90 up, perpendicular to each other, that is 0. It means they are not at all related. So when the value are more towards 1, it is more similar because angle between them is less. Now look at these numbers. Sentence 1 and 2, which speaks both about ML, have high cosine similarity, while sentence 1 and 3, where one speaks about ML and another speaks about pizza, they have lower similarity. But if you goes to equivalent distance, 1 and 2 have small distance. That's why they are close together. while 1 and 3 have large distance. That's why they are far apart from each other. And this is exactly what you want. The embeddings capture the first two sentences are semantically related, while the third sentence is different from the 1 and 2. And 1 and 2 are similar even though they are using different words. So it is capturing the context. Now see a practical example where we will try to build a search system where we have one query called as how do neural networks learn, and we have four responses, and we'll see which response is more similar to that query, or we will see try to find the best response for that query. For that, first I am creating embedding of the query vector separately and all the embeddings of that four responses separately. And I am trying to calculate the cosine similarity between each query and each response. And I will compare, and whichever will have the highest score, that will be the best response to that. Let me run it. If you see, the system correctly identified that neural network document is most relevant. Because if you see the question, how neural network learns, theoretically, neural network use backpropagation register. That is correct. And that's why it has high score towards 1, that is 0.92. While PISA and forecast response have less score. Here, if you see, deep learning model also has 0.88. Although it is not the correct response, but deep learning models are somewhat similar to neural networks because neural networks are part of deep learning models. So it has high score. So sometimes you may have some unrelated responses, but they are similar. So for that, we use something called as threshold value in any of the search system. So that here I will put my threshold value as zero point 0.9. Whatever the value greater than zero point 0.9, I will only compare them. You may sometimes use 0.95 depending upon what kind of use case you have, what kind of responses you are getting. So threshold always help you because sometimes what you will have four completely unrelated responses, such that maybe the high score is zero point 0.6 or zero point 0.5. If you take always the highest value, then it is also wrong. So that's why we need threshold value. And this is why embeddings are the foundation of whatever the AI use case you see, be it semantic search, be it recommendation system, be it retrieval augmented generation, any AI use case that needs to understand text, that need to understand semantic relation between text, not only words, not only word label or character label. You to understand the relationship between the text. What is the meaning of the sentence? We need embedding. So any modern AI application, be it RAG, agent, whatever you see, every use case need embeddings. Now let's talk about how LangChain standardizes working with embedding. Till now, if I have see for every creating embeddings of any text, I am using embed query. So what does embed query does? It creates single embeddings for single sets of text or single paragraph of text. That's why for all the four responses, I'm running them in loop. But there is one more another standardized interface that is embed documents that will create the embeddings for all the sets of text in one shot. If you see here, I am using embedding documents and it already created three documents in one shot. I'm not using any for loop. So this is more optimized way. You can still use embed query. That is not that is not the wrong way. That is also correct. But this is more optimized way, which will help you to process multiple text in efficiently. As you understand what embeddings is and how to create embeddings, now let's see one of the most crucial which is used for in many of the production applications, that is caching embedding. Because many times you will generate embeddings that cost money and time. If you are using OpenAI, you are paying per token embedded. If you are embedding the same text multiple times, you are wasting your money. For example, you have 1,000 documents in a knowledge base. Every time you app restarts, you need to re-embed those all 1,000 documents. That's expensive and very slow. That's why we need to cache the embeddings. Caching means we will store the already created embeddings in some place. It may be your database, it may be your local file store, it may be anywhere, right? It not only about that you store in local, you may store in Redis, you may store in a database. Okay, so Let me first import, and first I need to create a local file store where I will store my embeddings. Then I'm creating a caching embedding. First I am passing my embedding model, then I'm passing my location where I will store, then I'm passing namespace. Namespace means it will just use as a prefix to my cache keys, just to avoid confusions between multiple caching if happens with multiple models. And batch size is how many documents to embed before you write into cache. Okay, let me run this. Okay, now let me run for the first time. So there is no cache. It has not been documented yet, right? Let me run it. So what I am doing it, how many documents I am taking? Okay, I am now have 30 documents where same three document is repeating 10 times, so that we can understand the caching part properly. Let me first get the documents. So here you see it is taking 0.036 seconds. Okay, now you have see I have cached three documents. So it is taking 1.51 time. 515 and testing with 30 documents, and it took total 1.515 seconds, and it total cached 3 documents. See, I am embedding 30, but it is only caching 3 because same 3 documents are repeating. So that even if I am for first time also I am repeating same document multiple times, it is not caching them. So it is saving my storage. That is my first advantage. Second advantage is, let me run it for second time. Okay, if you see, first time it took 1.515 seconds, second time it took 0.035 seconds. It is 43 times faster. So now when I am trying to create using caching embedding, when I am trying to create the embedding, it is not creating embeddings, it is just retrieving those keys. So that's why it is 43 times faster. So we saw two advantages. One is storage, second is speed. Now let's understand how caching works. How cache is getting created in a backend. Okay, so there is something called as hash key that will create it. So if you have the same text, same hash will create and cache will hit when the next time the same text is getting embedded. But if you have different text, different hash will created, so cache will get missed. So any small changes to your text, it will create some different hash. If you see here, it is my, these are the three cache I did, right? And if you see here, these are the three cache keys. And if you see, if you remember, I have created one namespace. So it is getting that particular namespace here. And then it is getting that hash keys. Now there is one more option also. You can cache also queries. Till now I am only caching the documents. Now I can cache both document and queries as well. So for that there are two options. One is you can use the same store where you are storing the documents, you can store their queries by just making it true. But if you want, you can create separate store as well for queries. Now you can ask why separate store is needed if I can store in the same place, because queries are typically shorter and more varied, while the documents, which are the responses, are generally longer and mostly static. Okay, so sometimes you might want different kind of policies to deal with queries and document. So there is no hard and fast rule. It all depends on use case. But this is a generalized trend that you can. It is always better to create separate store if you have the sufficient storage with you. Now let's create a RAG application from scratch. Without using anything, we'll create a RAG application. Okay, where we're using three documents that will get embed and we'll cache it. Then we'll have three queries and we will cache these queries also because I have two repeated queries. Okay, if you see here, it is created three embedding documents, right? Those three are getting cached. That's correct because I have three different documents here, but I have three queries, out of which two queries are same, right? So that's why when I'm processing these queries, you can see here, first query it took 0.330 seconds, second query is a new query, that's why it took 0.31 second, but third query, what is LangChain? It is same as the first query. That's why cache got hit and it is taking only 0.0013 seconds. Okay. So it means the documents are embedded once and cached forever until they are changing it. And common queries also are getting cached and used. Sometimes what will happen? Customers keep asking the same question multiple times. So why to waste so much of cost on the same query? You can cache those common queries. So it is helping you. First of all, it is saving your time, that reduce latency, and it can save your money as well. That is your cost. And at the end, always remember, whenever your requirement is completed, you can clear the cache as well to free up the store space. Now let me show you how to interact with other models. Till now, whatever we have saw, all are with Gemini. Now let me show how to interact with OpenAI. So this is one of the OpenAI web. So here I'm taking text embedding 3 small and using embed query. See, now you would just need to swap the model. Now in place of this, if I will create another model, I will just replace it here. No need to go through all this process again, right? If I take this model and place it in my above code also, it will run. That is the advantage of using LangChain, because it is using a unified interface. But if you will use all those models separately, every model has a different format. You need to keep the text format in different way. Okay, so this is now how we're getting. Now we can see similarly for hugging face also, right? We can create for hugging face also an open source model, but again using endpoints. But how to connect with hugging face a local model by downloading them, I have already explained them in my LangChain LLM models video. And there you have it. We learn embeddings, what are embeddings and why they matter, how vector captures semantic meaning, and how similarity metrics for comparing embeddings. And also we saw how the LangChain's unified embedding interface and some of the powerful caching strategies for production application. Everything demonstrated with live code so you can see exactly how it works. If you found this helpful, smash the like button and subscribe for more such tutorials. And turn on the bell notification so don't miss the upcoming videos. Drop the comment if you have any questions or you want to see any specific topics to be covered. The code from this video is in the description below, so start experimenting. Thanks for watching. I will see you next one. Till then, keep learning, keep coding, and keep growing.